In this lecture, we're going to look at states of matter and relationships between them from a physical and energy perspective. There are really three different states of matter that we deal with in chemistry. There are gases, liquids, and solids. Gases are, of course, compressible fluids. Right? A gas will take the shape of its container. And they're compressible. We looked at in Chapter 5 a lot about changing volumes and pressures of gases. So the gases are compressible because there's a lot of space between the molecules or particles that make up the gas. Liquids are also fluids, but they're relatively incompressible. All right, so they're fluid, but they're relatively incompressible fluids. And then solids are, of course, are rigid. The particles sort of vibrate around fixed sites. Okay, not so compressible. Within these, let's think from a very broad perspective about the energies involved. In gases, the kinetic energy of the particles is much greater than the attractive forces between the particles. So in gases, again, kinetic energy of the particles is much greater than the attractive forces that are between the particles. With solids, the attractive forces are greater than the kinetic energy of the particles. So the attractive forces between the particles are greater than the kinetic energy of the particles. That's a good frame of mind to have when it comes to thinking about the energies that are involved in these different states of matter. Here's an image from your textbook, figure 11.2. Gases have a lot more space between them, of course. That's what makes them compressible. Liquids the molecules are closer together. The kinetic energies of gases is very high. The kinetic energies of solids is relatively lower. In solids, the attractive forces between the particles is greater than the kinetic energy of the particles. Liquids are in the middle. Liquids are somewhat compressible. Let's think about the changes of state that you can have between these things, between the different states. And one of the best images to have, or is in your textbook on this. This is figure 11.3. But let's look at these different changes of state. That we can have between different states of matter and what they're called. Many of these you're familiar with just from colloquial language, but some of them are maybe new. For example, so let's start with a solid. If we take a solid and bring it into the liquid phase, it's called melting. That's what we call it. So a solid can melt and become a liquid. A liquid can become a solid, and we call that freezing. And again, that's pretty familiar it should be pretty familiar to you. We're just colloquially talking. We freeze something or we melt something and so on. We can have a liquid, and we can take it into the gas phase, and that is called that process is called vaporization. We can go in the other direction. We can take a gas, condense it, and it becomes a liquid. We say we have, if you have a cold drink on a humid day, there's condensation that occurs on the glass. So what's happening is the water from the gaseous water from the atmosphere is condensing into a liquid onto your cold glass. We can also go directly from a solid to a gas for some materials. That's called sublimation. Again, you're familiar with sublimation. Dry ice sublimes from the solid directly to the gaseous state without having a liquid state in between them at atmospheric pressure and temperature. Also, we can go from a gas to a solid directly too. We call that deposition. Sometimes it might be called condensation, but typically we called deposition. All right, so these are just some terminology that we're going to be using when we talk about these things. Let's have another piece of terminology. The melting point of a substance. The melting point of a substance is the point at which a crystalline solid changes to a liquid. It melts. Okay. Sometimes you might hear people talking about something called the normal melting point. All that means is that the pressure under which this process is happening is at 1 atmosphere of pressure. So the melting point is the temperature at which a solid becomes a liquid. Sometimes we also talk about sometimes people talk about a liquid having a freezing point. The freezing point and the melting point are really exactly the same thing. It's just we're talking about things going from one direction to another. Let's think next about heats of phase transitions. So what's happening when we melt or vaporize or condense? Let's think about the energetics of those processes. So heat's a phase transition. So the energy's involved. Okay. So as we talked about, so going from a less ordered state. So for example, a solid, a liquid, to a gas. What we have to do is we have to put energy into the substance. Energy must be absorbed. We saw a moment ago that in gases, the kinetic energy of the particles is greater than the attractive forces between the particles. In solids, the attractive forces between the particles is greater than the kinetic energy of the particles. So it makes sense to go from a solid to a liquid to a gas. We have to put energy into the material to overcome these attractive forces between the particles themselves. Let's look at some of these heats. The heat of fusion is the energy required to bring a transition from the solid to the liquid state at the melting point. So it is the energy It's the energy required to bring a transition from the solid state to a liquid state at the melting point. This is figure 11.3 again. Note that so we don't call it heat of melting, we call it heat of fusion. Fusion is just another way of talking about going from a solid to a liquid. That's where the heat of fusion comes from. So heat of fusion, solid to liquid, it's that energy that's required. Just to give you an idea of the magnitude of the energy, to go from water, ice water, solid, to liquid water, the delta H of fusion is 6 kilojoules per mole. Let's look at the heat of vaporization. So this is the energy required. To convert a liquid to its vapor. Just again to give us an idea of the energy that are involved in this. Water liquid to water gas, the delta H of vaporization is 40 kilojoules per mole, 40.7 kilojoules per mole. So it's about nearly 10 times higher to go from, in energy, to go from a liquid to a gas than it is to go from a solid to a liquid. Gases have a lot of kinetic energy. They have a lot of kinetic energy in them. And so we see that in the actual data. Okay. So and then now this is a relatively straightforward thing, but let's think for a moment about the heat of sublimation. Okay. Delta H of sublimation would be quite simply the energy required to convert a solid to the vapor. So with heat of sublimation, we're going from a solid directly to the gas phase. And what do you think the delta H of sublimation would be? So H2O solid to H2O gas. Use Hess's law. We just add these two up, right? So the delta H of sublimation would be simply the sum of those things. So 46.7 kilojoules per mole. Let's look at a diagram that will help us illustrate the heats involved and the energies involved in changing phases. This is figure 11.9 from your textbook. In figure 11.9 from your textbook, what this is illustrating is there are a couple of things. So let's look at what's happening here. Here on this axis we have time, and we're adding heat at a constant rate. So what you can think of is energy being put in over a constant rate as we go along from zero to more energy. So energy is being put into our, in this case, they've got it labeled for ice and water, liquid water, ice, steam, and so on. And then let's look at the temperature here. That's what's happening here. Now there's one thing I want to point out, is that there's no change in temperature. There's no change in temperature during phase transitions. So let's take and we'll see this in a moment. That's what these flat lines are indicating. No change in temperature during phase transitions. Okay, so let's start here at this point on our graph and think about what's happening. Our liquid, our block of ice, our ice cube, if you will, is at minus 20 degrees Celsius. We start to add energy at a constant rate. And the slope of this line is simply going to be determined by the heat capacity of solid ice, or solid water. So the heat capacity of the solid ice will determine the slope of this line. In other words, how fast the temperature changes depending on how much energy you've put into it. And then once we reach 0 degrees, which is the normal, and at 1 atmosphere, normal melting point of ice. At that point, what's happening is we're starting to put energy into our solid to melt it into the liquid phase. Now, because of the heat of fusion, the energy required to bring a transition from the solid to the liquid at a melting point, we have both ice and water existing at the same temperature. For this given amount of ice, this given amount of solid water, we had to add this much energy in order to completely melt it. So at this point we have this is what's called a phase transition. Now, when we melt all of the ice and we have simply water at 0 degrees Celsius, we're continuing to add heat as we move along. As we add more heat, the water is going to get warmer and warmer. The slope of that line is going to depend on the specific heat of the water, the heat capacity of the water. And we're going to heat that water up until it reaches 100 degrees Celsius. And then at that point, we've reached what would be called the boiling point. And then we start to put into the water the heat of vaporization. Energy is required from going from a liquid to a gas. So at 100 degrees Celsius, we're adding energy. The heat of vaporization is now being added. Now, one thing to keep in mind, one thing I told you about liquid water is that the heat of fusion is about 10 times smaller than the heat of vaporization. And you can see that in this graph. It takes about 8 to 10 times more energy to bring all of our water into the gas phase and to make it all steam. The no change in temperature during phase transition, that's when we're putting all of our heat energy into the heat of vaporization, in this case, the heat of fusion down here. So as we're increasing the temperature, or as we're increasing the amount of heat putting into our system, our water is still at 100 degrees until all of it becomes steam. All of it becomes a vapor, a gas. At that point, we can continue to put heat into our system, and the slope of this will again depend on the heat capacity of gaseous water.